Here's a question that has puzzled even brilliant physicists. If nothing can escape a black hole, not even light, then how does its gravity get out? This paradox touches the very heart of how gravity works, and the answer will revolutionize your understanding of space, time, and the fabric of reality itself. Think about it. If gravity needs to somehow reach out from inside the black hole to pull things in, but nothing can escape the event horizon, how do objects outside know to fall toward it? If you're fascinated by these mind-bending mysteries of the cosmos, make sure to subscribe to this channel and give a thumbs up. Your support helps me explore the deepest questions in physics. One quick question. If you could ask the universe one question and get a real answer, what would you ask? Let me know in the comments down below. I will choose the most creative answer. Now let's begin. This paradox seems to create a logical impossibility. We know black holes have immense gravitational pull. We've observed stars orbiting invisible massive objects at incredible speeds. The star S2 near our galaxy's central black hole, Sagittarius A star, reaches speeds of 7,600 kilometers per second. We've watched matter spiral into black holes, heating up to millions of degrees before disappearing beyond the event horizon. Clearly, black holes exert gravity on their surroundings. But here's the puzzle. Einstein showed us that nothing can travel faster than light, and black holes are defined by having escape velocities exceeding light speed. The event horizon is precisely the boundary where even light can't escape. So if gravity is a force that needs to propagate from the black hole to external objects, and if this force can't travel faster than light, how does it get past the event horizon? The answer requires us to completely reimagine what gravity actually is. Newton thought of gravity as a force, an invisible string pulling objects together. In his view, the sun pulls on Earth across 93 million miles of empty space. This worked beautifully for calculating orbits and predicting celestial motions. But it had a fatal flaw that Newton himself recognized. How does this force act instantly across vast distances? Einstein solved this puzzle in 1915 with general relativity, but his solution was so radical that even today it challenges our intuition. Gravity isn't a force at all. It's the curvature of space-time itself. Mass and energy don't pull on distant objects. Instead, they bend the fabric of space and time around them. Objects follow the straightest possible paths through this curved space-time, which we perceive as gravitational attraction. This distinction is crucial for understanding our black hole paradox. A black hole doesn't need to send gravity signals out past its event horizon because gravity isn't a signal, it's the shape of space-time itself. The black hole curved space-time when it formed, and that curvature exists outside the event horizon. External objects respond to the space-time curvature where they are, not to signals from inside the black hole. Think of it like this. Imagine a heavy bowling ball on a stretched rubber sheet. The ball creates a depression in the sheet. Now cover the bowling ball with an opaque dome. The depression in the sheet still exists outside the dome, even though you can't see the ball. Objects rolling near the dome will still curve toward it, following the depression in the sheet. They're not responding to a force from the hidden ball. They're responding to the shape of the sheet where they are. This analogy, while helpful, is actually too simple. In reality, black holes curve four-dimensional space-time, not just a two-dimensional surface. They bend both space and time, creating effects far stranger than any rubber sheet could demonstrate. Near a black hole, time itself slows down. Space becomes so distorted that straight lines curve back on themselves. The event horizon isn't a physical barrier but a point of no return in this extremely warped space-time. The key insight is that the space-time curvature outside a black hole was established when the black hole formed. When a massive star collapses, it curves space-time around it. As the star shrinks below its Schwarzschild radius, and forms an event horizon, the exterior space-time curvature remains. It's like the gravitational field is frozen outside the event horizon at the moment of collapse. This frozen field concept was demonstrated mathematically by David Finkelstein in 1958. He showed that the Schwarzschild solution, the mathematical description of spacetime around a non-rotating black hole, is static outside the event horizon. The gravitational field doesn't change, doesn't need updating, and doesn't require any communication from inside the black hole. But this raises another question. What if something falls into the black hole, increasing its mass? How does the external gravitational field know to get stronger? This brings us to an even deeper aspect of general relativity. Changes in the gravitational field do propagate outward, but they propagate as ripples in spacetime itself, gravitational waves that travel at the speed of light. Here's the beautiful resolution. When matter falls toward a black hole, it affects spacetime curvature outside the event horizon before it crosses inside. As matter approaches the horizon, it increasingly warps the external spacetime. By the time it crosses the event horizon, all its gravitational effects have already been imprinted on the exterior spacetime. The external universe has already felt the mass addition before the matter disappears inside. The LIGO and Virgo gravitational wave detectors have actually observed this process in action. When they detected the merger of two black holes in event GW1F914, they were measuring ripples in spacetime caused by the violent reorganization of spacetime curvature as two black holes spiraled together and merged. The gravitational waves were produced outside the event horizons, carrying information about the mass and spin of the final black hole. This detection, announced in 2016, provided direct confirmation that gravitational effects propagate at light speed, not instantaneously. It also showed that black hole mergers follow Einstein's predictions precisely. The external spacetime adjusts smoothly as the black holes merge, with all changes propagating outward at light speed, never requiring any signal from inside the event horizons. To truly understand how gravity escapes a black hole, we need to dive deeper into what spacetime actually is. This isn't just empty space with clocks ticking. It's a dynamic, flexible fabric that can stretch, compress, twist, and ripple. Every mass, every concentration of energy leaves its mark on this fabric. And once that mark is made, it exists independently of what created it, like a footprint in sand remains even after the foot has moved on. John Wheeler, the physicist who coined the term. Black hole famously said, "Matter tells spacetime how to curve, and spacetime tells matter how to move." This elegant summary captures the essence of general relativity. But it also hints at our resolution. The curvature of spacetime exists as a field throughout space, not as a series of signals emanating from masses. Let's explore what this really means. In electromagnetic theory, we have electric and magnetic fields that permeate space. A charged particle creates an electric field around it, and this field exists at every point in space, getting weaker with distance. Crucially, the field at any point depends only on what charges were there in the past, accounting for the light travel time. The field doesn't require continuous communication with the charge. Gravitational fields work similarly, but with a profound difference. While electromagnetic fields exist within space-time, the gravitational field is space-time. The curvature of space-time at any point is the gravitational field at that point. This isn't just a mathematical abstraction, it has real, measurable effects that we observe every day. GPS satellites must account for gravitational time dilation, the fact that clocks run faster in weaker gravitational fields. This isn't because gravity is pulling on time, it's because the satellites exist in a region of space-time that's less curved than Earth's surface. Their clocks aren't malfunctioning, they're faithfully measuring the flow of time through their local spacetime geometry. The Gravity Probe B mission, launched in 2004, provided extraordinary confirmation of how mass affects spacetime. This satellite carried 4 of the most perfect spheres ever manufactured, gyroscopes that could detect incredibly subtle changes in spacetime. It measured 2 effects predicted by Einstein: the geodetic effect, how Earth's mass curves spacetime, and frame dragging, how Earth's rotation twists spacetime. The results, published after years of analysis, matched Einstein's predictions perfectly. Earth doesn't just attract objects, it literally bends and twists the fabric of reality around it. And this bending and twisting exists as a field throughout space, not requiring any ongoing communication from Earth's mass. Now let's apply this understanding to black holes. When a massive star exhausts its nuclear fuel, it can no longer support itself against its own gravity. The collapse happens catastrophically. In less than a second, the core shrinks from thousands of kilometers across to just a few dozen. During this collapse, the space-time curvature around the star changes dramatically. But here's the crucial point: these changes propagate outward at the speed of light. The space-time at any distance from the collapsing star only knows about changes that have had time to reach it. By the time the star collapses within its event horizon, the external spacetime has already adjusted to the new configuration. The curvature pattern outside the event horizon is established and remains frozen in place. This freezing of the external gravitational field has been studied extensively through numerical relativity, using supercomputers to solve Einstein's equations for dynamic situations. Simulations of black hole formation show that once the event horizon forms, the external spacetime settles into a stable configuration described by just 3 properties: mass, electric charge, and angular momentum, spin. This is the famous no-hair theorem. Black holes have no other distinguishing features. All the complex details of the collapsing matter, its composition, structure, temperature, are hidden behind the event horizon. The external universe only sees the total mass, charge, and spin encoded in the space-time curvature outside the horizon. Stephen Hawking's work in the 1970s revealed an even deeper truth about black hole horizons. The event horizon isn't just a point of no return, it's a boundary in space-time with profound quantum mechanical properties. The horizon has a temperature and entropy, and it slowly evaporates through Hawking radiation. But even this radiation originates from just outside the horizon, not from within. The holographic principle, developed by Gerard 't Hooft and Leonard Susskind, suggests something even more radical. All the information about what fell into a black hole might be encoded on the 2-dimensional surface of the event horizon, not in the 3-dimensional volume inside. If true, this means the inside of a black hole might not even exist in the way we normally think about space. Recent observations have given us unprecedented views of black hole spacetime. The Event Horizon Telescope's image of the black hole in galaxy M87, released in 2019, shows the shadow cast by the event horizon. The glowing ring we see is light from hot gas swirling outside the horizon, its path bent by the extreme space-time curvature. The dark center isn't the black hole itself. It's the region where space-time is so curved that light paths spiral inward. The image confirms that space-time around black holes behaves exactly as Einstein predicted. The size and shape of the shadow match calculations based on the mass and spin of the black hole. We're literally seeing the curvature of space-time made visible through its effect on light. But what about quantum mechanics? Doesn't the uncertainty principle require some quantum fluctuations to escape the black hole? This question led to one of the deepest puzzles in physics, the black hole information paradox. If nothing can escape a black hole classically, but quantum mechanics requires information to be preserved, what happens to information that falls in? The current understanding, still debated, is that information is preserved but scrambled in incredibly complex ways. The information might be encoded in subtle correlations in the Hawking radiation, or it might be stored holographically on the horizon. But crucially, none of these mechanisms require faster-than-light communication from inside the black hole. Virtual particles, which mediate forces in quantum field theory, add another layer to our understanding. The graviton, the hypothetical quantum particle of gravity, would be a spin-2 massless boson. But even gravitons respect the black hole's event horizon. Virtual gravitons mediating the gravitational force exist throughout spacetime, but they don't need to escape from inside the black hole to create the external gravitational field. The relationship between gravity and time brings us to one of the most profound aspects of black holes. Near the event horizon, time itself behaves in ways that challenge our everyday understanding. This extreme time dilation is intimately connected to how gravity escapes, or rather, why it doesn't need to escape at all. Understanding this connection reveals the true nature of spacetime and gravity's role as geometry rather than force. As you approach a black hole, time dilation becomes increasingly severe. At the event horizon itself, time dilation becomes infinite from the perspective of distant observers. This means that from our viewpoint far from the black hole, anything falling in appears to slow down and freeze at the horizon, its light red-shifted until it fades from view. Yet from the falling object's perspective, it passes through the horizon normally, experiencing finite time. This time dilation is a direct consequence of space-time curvature, the same curvature that creates what we perceive as gravity. In flat space-time, everyone agrees on the rate of time flow. But in curved space-time, time flows at different rates, depending on your position in the gravitational field. The stronger the gravity, more precisely, the more curved the space-time, the slower time flows relative to regions of weaker gravity. If you're fascinated by these relativistic effects on time, you might want to check out my video called "Does Time Stop When You Hit the Speed of Light?", where I explore how motion through space affects your journey through time. The physics that makes time stop at light speed is intimately connected to why time nearly stops at black hole event horizons. Both are extreme examples of how space-time geometry governs our universe. The link is in the description below and on the card above. Now let's see how this connects to our gravity paradox. The GPS system provides everyday proof of gravitational time dilation. Satellites in weaker gravitational fields experience time flowing about 45 microseconds per day faster than clocks on Earth's surface. This tiny effect, if not corrected, would cause navigational errors of about 11 kilometers per day. The satellites aren't broken. They're experiencing the natural flow of time through less curved spacetime. Near black holes, these effects become extreme. At the event horizon of a stellar mass black hole, the gravitational time dilation factor becomes infinite. This means that from our external perspective, time at the horizon has stopped. Nothing ever appears to cross the horizon from our viewpoint. Everything freezes at the boundary, its light infinitely red-shifted. This creates a profound insight into our original question. The gravitational field we observe outside a black hole is, in a sense, a fossil, a preserved imprint of the collapsing matter from our time perspective. From our viewpoint, the matter that formed the black hole is still frozen at the horizon, never having crossed inside. The external gravitational field is the field of this frozen configuration. But wait! Doesn't this contradict the fact that black holes can grow by swallowing matter? How can the external field strengthen if nothing ever crosses the horizon from our perspective? The resolution is subtle and beautiful. As matter approaches the horizon, it contributes increasingly to the external space-time curvature. By the time it reaches the horizon, from our perspective, it has already deposited all its gravitational influence on the external field. Think of it like this. As matter falls toward the black hole, it continuously updates the surrounding gravitational field. These updates propagate outward at light speed. The closer the matter gets to the horizon, the more its gravitational contribution resembles that of matter at the horizon. In the limit, there's no observable difference between matter frozen at the horizon and matter that has crossed inside. The Schwarzschild solution, discovered by Carl Schwarzschild in 1916 while serving on the Russian front in World War I, describes space-time around a non-rotating black hole. Remarkably, this solution is static. It doesn't change with time. This might seem paradoxical for an object formed by collapse, but it reflects the fact that from our external perspective, the collapse asymptotically approaches but never reaches a final state. For rotating black holes, described by the Kerr solution discovered in 1963, the situation is more complex but follows the same principles. The rotation drags space-time around with it, an effect called frame dragging. This creates an ergosphere outside the event horizon where space-time itself is pulled around faster than light relative to distant stars. Yet even this complex space-time geometry is static from our external perspective. The membrane paradigm, developed in the 1980s by Kip Thorne and colleagues, provides another useful way to think about black holes. From the external observer's perspective, the black hole can be modeled as having a membrane at the horizon with specific electrical resistance, viscosity, and other properties. This membrane can carry currents and charges, explaining how electromagnetic fields behave near black holes without requiring any communication from inside. Numerical relativity simulations have revolutionized our understanding of dynamic black hole spacetimes. When two black holes merge, the spacetime goes through violent distortions, emitting gravitational waves. Yet throughout this process, no signals need to escape from inside either event horizon. The waves are generated by the dynamic spacetime in the region outside the horizons. The ring-down phase after merger is particularly revealing. The merged black hole vibrates like a struck bell, emitting gravitational waves at specific frequencies determined by its mass and spin. These quasi-normal modes are entirely determined by the external spacetime geometry. The interior of the black hole, whatever its nature, doesn't affect these vibrations. Recent advances in our understanding come from studying extremal black holes, those with maximum possible spin or charge for their mass. These push the limits of black hole physics, with their inner and outer horizons nearly coinciding. Yet even in these extreme cases, the external gravitational field behaves according to the same principles, determined entirely by the space-time geometry outside the horizon. The firewall paradox proposed in 2012 challenged our understanding of black hole horizons from a quantum perspective. If information is preserved in black hole evaporation, then the horizon might not be the smooth boundary Einstein envisioned, but a region of high-energy quantum fluctuations. Yet even these proposed firewalls would exist at, not inside, the horizon, preserving the principle that nothing needs to escape from inside. The soft hair proposal by Hawking, Perry, and Strominger suggests that black holes might have more features than just mass, charge, and spin. They might have soft hair in the form of zero-energy gravitons or photons at the horizon. These would be features of the horizon itself, not the interior, again consistent with our understanding that the external gravitational field depends only on the external space-time structure. The detection of gravitational waves has given us an entirely new way to understand how gravity behaves around black holes. These ripples in spacetime, first detected by LIGO in 2015, carry information about the most extreme gravitational events in the universe. When black holes merge, they create a symphony of spacetime distortions that teaches us exactly how gravitational effects propagate and why they don't need to escape from inside event horizons. On September 14, 2015, at 9:50 a.m. UTC, both LIGO detectors recorded a signal that had traveled 1.3 billion years to reach Earth. This first gravitational wave detection, GW1Fib114, came from two black holes spiraling together and merging. The black holes, about 30 and 35 times our Sun's mass, combined to form a single black hole of 62 solar masses. The missing 3 solar masses, equivalent to 3 suns, was converted entirely into gravitational wave energy in less than a second. This detection answered our question definitively. Gravitational information travels at exactly the speed of light, not faster. If gravity were instantaneous, as Newton thought, we would have detected the merger's gravitational effects billions of years before the waves arrived. Instead, the gravitational waves traveled alongside light, taking the same time to reach us. This confirms Einstein's prediction that changes in gravitational fields propagate as waves through spacetime at light speed. But here's what's crucial for our paradox. Throughout the entire merger, no gravitational information escaped from inside either black hole's event horizon. The gravitational waves were produced entirely by the dynamic spacetime outside the horizons. As the black holes spiraled closer, they stirred spacetime like cosmic mixers, creating waves that rippled outward. The horizons grew and eventually merged, but always the wave generation happened outside. The waveform of a black hole merger tells a precise story. During the in-spiral phase, the two black holes orbit each other, gradually losing energy to gravitational waves and spiraling closer. The frequency increases, a characteristic chirp that rises in pitch. Then comes the merger itself, where the horizons touch and combine. Finally, the ring-down phase where the merged black hole settles into its final state, vibrating at specific frequencies like a struck bell. Each phase teaches us about black hole gravity. The in-spiral shows how black holes interact gravitationally over large distances. The merger reveals what happens when event horizons combine. The ring-down demonstrates how a perturbed black hole returns to equilibrium. Throughout all phases, physics happens entirely outside the horizons, in the realm of accessible spacetime. LIGO and Virgo have now detected over 90 black hole mergers, each confirming the same physics. The European Space Agency's LISA mission, planned for the 2030s, will detect gravitational waves from supermassive black hole mergers. These future observations will probe even more extreme regimes where black holes millions of times our Sun's mass dance around each other and merge. The information content of gravitational waves deserves special attention. When LIGO detects a merger, it extracts specific information, the masses of the original black holes, their spins, their distance from us, and properties of the final merged black hole. This information was encoded in the ripples of space-time outside the event horizons. No information from inside the black holes reaches us, nor needs to. Consider what happens during the ring-down phase. The merged black hole vibrates in specific patterns called quasi-normal modes. These are like the fundamental frequencies of a musical instrument, but instead of sound waves in air, they're waves in space-time itself. The frequencies depend only on the final black hole's mass and spin, not on any details of what's inside. It's as if the black hole has forgotten everything about how it formed except these basic properties. This forgetfulness is formalized in the no-hair theorem. A black hole is characterized completely by just 3 numbers: mass, electric charge, and angular momentum. All other information about the matter that formed it is hidden behind the horizon. From outside, two black holes with the same mass, charge, and spin are absolutely identical, regardless of whether one formed from collapsed hydrogen and the other from collapsed iron. The black hole information paradox challenges this simple picture from a quantum perspective. Quantum mechanics says information cannot be destroyed, yet black holes seem to swallow information forever. Hawking radiation, the quantum evaporation of black hole, appears thermal and random, carrying no information about what fell in. This creates a profound conflict between general relativity and quantum mechanics. Recent theoretical advances suggest the information might be preserved in subtle quantum correlations in the radiation or encoded holographically on the horizon. The important point for our gravity question is that none of these resolutions require information to escape from inside the black hole. The information, however it's preserved, must be accessible from outside the horizon. ADS-CFT correspondence, proposed by Juan Maldacena in 1997, provides a radically different perspective. In certain theoretical spacetimes, a gravitational theory in a volume is exactly equivalent to a quantum theory on the boundary of that volume. Applied to black holes, this suggests that everything about a black hole's interior might be encoded on its two-dimensional horizon. There might not even be a meaningful inside in the way we usually think. This holographic perspective aligns perfectly with our understanding of black hole gravity. If all the physics is encoded on the horizon, then of course the gravitational field outside depends only on the horizon properties, not on any supposed interior. The black hole's gravity doesn't need to escape from inside because, in a fundamental sense, there might not be an inside, just a boundary with all the information encoded on it. Observational evidence supports this picture. When matter falls toward a black hole, we observe its gravitational effects right up to the horizon. X-ray telescopes see hot gas spiraling inward, and we can measure the gravitational redshift of spectral lines. The gravitational field smoothly increases as matter approaches the horizon, with no discontinuity or mystery at the boundary. The Event Horizon Telescope has given us direct images of black hole shadows, the regions where gravity is so strong that light cannot escape. The size and shape of these shadows depend on the space-time geometry outside the horizon. The spectacular images of M87's black hole and our own Sagittarius A star confirm that space-time behaves exactly as Einstein predicted, with no surprises or paradoxes. At the intersection of quantum mechanics and general relativity lies perhaps the deepest insight into our paradox. The event horizon isn't just a classical boundary, it's a quantum mechanical entity with profound properties. Understanding how quantum effects operate at the horizon reveals new perspectives on why gravity doesn't need to escape and might fundamentally change our conception of what black holes actually are. Hawking's groundbreaking discovery in 1974 showed that black holes aren't perfectly black. They emit radiation due to quantum effects near the horizon. This Hawking radiation arises from the quantum vacuum, where virtual particle pairs constantly appear and annihilate. Near the horizon, the extreme space-time curvature can separate these pairs before they annihilate, with one falling in and one escaping as real radiation. Crucially, this radiation originates just outside the horizon, not inside. The escaping particles carry away energy, causing the black hole to slowly evaporate. For a stellar mass black hole, this process takes an unimaginable 10 to the 67 years, far longer than the current age of the universe. But the principle is profound. Black holes are quantum mechanical objects that interact with their environment through the horizon. The temperature of Hawking radiation is inversely proportional to the black hole's mass. Paradoxically, smaller black holes are hotter and evaporate faster. A black hole with the mass of a mountain would be white hot and would evaporate in seconds. This temperature isn't coming from inside the black hole, it's a property of the horizon itself, arising from the quantum fields in the curved spacetime just outside. The Unruh effect, discovered by William Unruh in 1976, provides another quantum perspective. An accelerating observer sees the quantum vacuum as a thermal bath of particles. Since gravity and acceleration are equivalent according to Einstein's equivalence principle, observers near a black hole horizon experience similar effects. The horizon has a quantum mechanical temperature, even in purely classical spacetime. This quantum nature of horizons suggests they're not just geometric boundaries, but dynamic quantum systems. The stretched horizon or membrane paradigm treats the horizon as a physical surface with electrical conductivity, viscosity, and other properties. From the outside observer's perspective, infalling matter doesn't disappear at the horizon, but gets scrambled and thermalized on this quantum membrane. Recent work on the firewall paradox has intensified debates about the horizon's nature. If black hole information is preserved in Hawking radiation, then quantum entanglement patterns suggest the horizon can't be smooth, as Einstein envisioned. Instead, it might be a region of high-energy quantum fluctuations, a firewall that destroys anything crossing it. While controversial, this wouldn't change our answer. Gravity still wouldn't need to escape from inside. The holographic principle takes this further. If all information about a black hole's interior is encoded on the two-dimensional horizon, then the three-dimensional interior might be emergent rather than fundamental. The gravitational field outside would naturally depend only on the horizon encoding, not on any independent interior. Gravity doesn't escape because there's nothing independent inside from which it needs to escape. String theory offers additional perspectives. In string theory, black holes can be understood as bound states of strings and branes. The microscopic degrees of freedom that account for black hole entropy are string theory states. These microstates all have the same macroscopic properties, mass, charge, and spin, explaining why all black holes with these parameters have identical external gravitational fields. The fuzzball proposal in string theory suggests black holes might not have traditional interiors at all. Instead, they might be fuzzballs. Quantum superpositions of string states that fill the entire region within the would-be horizon. If true, this would definitively resolve our paradox. There's no interior from which gravity needs to escape because the black hole is a quantum configuration extending to the horizon. Loop quantum gravity provides yet another perspective. In this approach, space-time itself is quantized at the Planck scale. Near the black hole center, quantum geometry effects might prevent the formation of a true singularity. Some models suggest a bounce where collapsing matter rebounds, potentially creating a white hole in the far future. But again, these interior modifications don't affect the external gravitational field. The black hole information paradox has driven much of this quantum gravity research. If information falling into a black hole is preserved, where is it stored? On the horizon, in subtle correlations in Hawking radiation, in baby universes. Each proposal maintains that information remains accessible from outside. It doesn't hide in an inaccessible interior. Recent proposals like soft hair and quantum hair suggest black holes might carry more information than just mass, charge, and spin. These would be quantum features of the horizon or near-horizon region, not properties of the interior. They would affect the detailed quantum state of Hawking radiation while preserving the classical external gravitational field. The ER-EPR conjecture by Maldacena and Susskind proposes a deep connection between quantum entanglement and spacetime geometry. Einstein-Rosen bridges wormholes might be equivalent to Einstein-Podolsky-Rosen pairs, entangled particles. Applied to black holes, this suggests the interior might be connected to the radiation via quantum wormholes, but again, no classical information escapes through these connections. experimental tests of quantum gravity effects near black holes remain challenging. However, observations of black hole shadows by the Event Horizon Telescope are approaching scales where quantum corrections might be detectable. Future space-based gravitational wave detectors might see signatures of quantum effects in black hole mergers. Primordial black holes, if they exist, might be small enough to show quantum gravitational effects. The resolution of our paradox from quantum gravity is clear. The horizon is where all the interesting physics happens. Whether it's a quantum membrane, a fuzzball surface, or something else, the horizon encodes everything needed to determine the external gravitational field. The classical notion of an interior separated from the exterior by the horizon gives way to a quantum picture where the horizon itself is the fundamental entity. This quantum understanding reinforces our classical resolution. Gravity doesn't need to escape from inside a black hole because at a fundamental level there might not be an inside in the classical sense. The black hole is its horizon, and the gravitational field is the space-time curvature this quantum horizon creates in its vicinity. Theory is essential, but science demands observational confirmation. Fortunately, the universe has provided us with numerous natural laboratories where we can test our understanding of how gravity behaves around black holes. From stellar mass black holes in binary systems to supermassive giants at galaxy centers, each observation confirms that gravity operates exactly as our resolution predicts, as space-time curvature that doesn't need to escape from anywhere. The first compelling evidence for black holes came from Cygnus X1, discovered in 1964. This system consists of a blue supergiant star orbiting an invisible companion. By measuring the visible star's orbital motion through Doppler shifts in its spectrum, astronomers determined the invisible object's mass, about 15 times our Sun's mass, far too massive to be a neutron star. The X-rays come from gas stripped from the visible star, heated to millions of degrees as it spirals into the black hole. What's crucial is that we can measure the black hole's gravitational field through its effect on the companion star, even though we can't see the black hole itself. The star's orbit tells us exactly how space-time is curved in its vicinity. This curvature exists stably in the space around the black hole. It doesn't require any ongoing signal from inside the event horizon. Our galaxy's center provides an even more dramatic demonstration. For over 20 years, astronomers have tracked stars orbiting Sagittarius A star, our central supermassive black hole. The star S2 completes an orbit every 16 years, approaching within 17 light hours of the black hole and reaching speeds of 7,600 kilometers per second, 2.5% of light speed. These observations, which earned Reinhard Genzel and Andrea Ghez the 2020 Nobel Prize in Physics, allow us to map space-time curvature near a black hole with extraordinary precision. We can predict each star's position years in advance using general relativity. The gravitational field is stable and predictable, showing no signs of needing to communicate with the black hole's interior. In 2018, the Gravity collaboration detected gravitational redshift in S2's light as it passed close to Sagittarius A star. This wasn't just Doppler shift from motion, it was the reddening predicted by general relativity as light climbs out of a gravitational well. The measurement matched Einstein's predictions perfectly, confirming our understanding of space-time geometry near black holes. Even more remarkably, in 2020, the same team detected the Schwarzschild precession of S2's orbit. Just as Mercury's orbit precesses around the Sun due to relativistic effects, S2's orbit precesses around Sagittarius A star. This precession depends on the precise shape of space-time curvature and matches theoretical predictions, further confirming that the external gravitational field behaves exactly as expected. the Event Horizon Telescope has given us the most direct view of black hole spacetime. The glowing ring in the images of M87's black hole and Sagittarius A star isn't the event horizon itself, it's the photon sphere, where light orbits the black hole. The dark shadow inside is where spacetime curvature is so extreme that light paths spiral inward. The size and shape of this shadow depend entirely on the external spacetime geometry. These images required combining radio telescopes across Earth to create a virtual telescope the size of our planet. The fact that we see exactly what general relativity predicts, no more, no less, powerfully confirms our understanding. The gravitational field creates the observed spacetime curvature without any need for signals from inside the horizon. X-ray observations reveal even more about black hole spacetime. As matter spirals inward through an accretion disk, it heats up and emits X-rays. The innermost stable circular orbit, the closest distance matter can orbit stably, depends on the black hole's spin. By analyzing X-ray spectra, we can measure this spin and map the spacetime geometry near the horizon. The iron K-alpha line, a specific X-ray emission from iron atoms, gets broadened and skewed by relativistic effects near black holes. The line profile tells us how fast matter is orbiting and how close it gets to the horizon. These observations show matter following exactly the orbits predicted by general relativity in the curved spacetime outside the black hole. Quasi-periodic oscillations, QPOs, in X-ray brightness provide another probe. These regular flickerings might come from hotspots in the accretion disk orbiting at specific frequencies. The frequencies match those expected for orbital motion and disk oscillations in the strong gravitational field. Again, everything happens in the external spacetime, following the curvature established by the black hole's presence. Black hole jets provide spectacular confirmation of frame dragging. Many black holes launch powerful jets of particles at near light speed. These jets align with the black hole's spin axis, and their power correlates with spin rate. The spinning black hole drags spacetime around with it, and this twisted spacetime helps launch and collimate the jets. All of this physics happens outside the horizon in the ergosphere. Tidal disruption events occur when stars venture too close to supermassive black holes. The star gets torn apart by tidal forces, creating a bright flare as the debris falls toward the black hole. The Zwicky Transient Facility and other surveys have caught dozens of these events. The light curves match theoretical predictions based on external spacetime geometry, showing how gravity operates in the strong field regime. Binary black hole mergers observed by LIGO and Virgo provide the ultimate test. As the black holes spiral together, they emit gravitational waves that carry detailed information about the spacetime geometry. The waveforms match numerical relativity simulations with extraordinary precision. Throughout the merger, all the physics happens outside the horizons. No information emerges from inside either black hole. The ring-down after the merger is particularly telling. The merged black hole vibrates at specific frequencies determined by its mass and spin. These quasi-normal modes are like fingerprints of the external spacetime. We can extract the final black hole's properties from these vibrations, confirming that the external field depends only on mass and spin, not on any interior details. Microlensing observations show black holes bending light from background stars. When a black hole passes between us and a distant star, its gravity focuses the starlight, causing a temporary brightening. The light curve of these events depends on the spacetime curvature around the black hole. Several stellar mass black holes have been discovered this way, their gravity revealing their presence across thousands of light years. Future observations promise even more insights. The Laser Interferometer Space Antenna, LISA, will detect gravitational waves from merging supermassive black holes. The extremely large telescope will track stellar orbits even closer to Sagittarius A star. The next generation Event Horizon Telescope will create movies of black hole shadows. Each observation will further test our understanding of how gravity operates near event horizons. Our journey to understand how gravity escapes black holes has led us to profound realizations about the nature of reality itself. The answer that gravity doesn't need to escape because it's the curvature of space-time rather than a force challenges our deepest intuitions about space, time, and causation. These insights extend far beyond black holes, reshaping our understanding of the universe and our place within it. The first philosophical shift is recognizing that space and time aren't just the stage where physics happens, they're dynamic participants in the cosmic drama. Before Einstein, space was thought to be absolute and unchanging, a fixed grid against which we measure positions. Time flowed uniformly for everyone, everywhere. Black holes shatter these comfortable assumptions, revealing space-time as a flexible, dynamic entity that responds to matter and energy. This dynamism means the universe is far more interconnected than Newton imagined. Every mass, every concentration of energy shapes the space-time around it. You're not just sitting in space, or you're sitting in curved space-time shaped by Earth, the Sun, the galaxy, and every massive object in the universe. The gravitational field isn't something extra added to space, it is the shape of space itself. The black hole paradox forces us to confront the nature of inside and outside. We typically think of these as obvious concepts. You're either inside a room or outside it. But event horizons challenge this binary thinking. From an external observer's perspective, nothing ever crosses the horizon. From an infalling observer's perspective, crossing is uneventful. Which perspective is true? General relativity says both are equally valid descriptions of reality. This relativity of perspectives extends to fundamental questions about existence. Does the interior of a black hole exist if it's causally disconnected from the rest of the universe? If no information can escape to confirm its existence, in what sense is it real? These questions echo philosophical debates about unobservable entities that date back to ancient Greece but take on new urgency in the extreme physics of black holes. The holographic principle suggests an even more radical possibility, that our three-dimensional experience might be emergent from information encoded on two-dimensional surfaces. If black hole physics is any guide, what we perceive as volume might be an illusion, with all the real information living on boundaries. This could extend to the entire universe, suggesting our perceived reality is a projection of something more fundamental. Time's behavior near black holes challenges our notion of temporal flow. We experience time as flowing from past to future, but general relativity reveals this flow as relative and observer-dependent. Near a black hole, time can slow to a crawl or maintain its pace, depending on your position and motion. The absolute time that grounds our everyday experience dissolves into a multiplicity of valid temporal perspectives. The information paradox highlights deep tensions between our major theories of physics. General relativity says information can be lost forever behind event horizons. Quantum mechanics says information must be preserved. This conflict isn't just technical. It touches on whether the universe has perfect memory, whether the past can be truly erased, whether determinism holds at the deepest level. Our resolution of the gravity paradox, that gravitational fields are features of space-time geometry established when black holes form, suggests a universe where effects can persist independently of their causes. The black hole's gravitational field continues to exist even though its source, from our perspective, is frozen at the horizon. This challenges simple notions of causation, where effects require ongoing connection to their causes. The no-hair theorem presents another philosophical puzzle. Black holes erase all information about their formation except mass, charge, and spin. A black hole made from hydrogen is identical to one made from uranium, if their basic parameters match. This ultimate simplicity emerging from arbitrary complexity suggests profound principles about information, identity, and distinguishability in nature. The possibility that black hole interiors might not exist in any meaningful sense, whether due to firewalls, fuzzballs, or holographic principles, challenges our assumptions about space itself. We assume space continues smoothly everywhere, but black holes might represent boundaries where our spatial concepts break down. The universe might be more like Swiss cheese than we imagine, with regions where space itself ends. These insights affect how we think about scientific knowledge itself. Black holes represent absolute limits to observation. By definition, their interiors are unobservable. Yet we can still say meaningful things about them through their external effects. This suggests science can productively study even fundamentally unobservable entities, as long as they have observable consequences. The role of mathematics becomes philosophically crucial. The equations of general relativity predicted black holes decades before any were observed. Mathematical consistency led to physical insight. This suggests mathematics isn't just a language for describing nature, but somehow participates in determining what can exist. The universe seems to respect mathematical elegance and consistency. Black holes also illuminate the relationship between local and global properties. Locally, near the horizon, physics seems normal to a freely falling observer. Globally, the horizon represents an absolute boundary. This tension between local and global perspectives appears throughout physics and suggests reality can't be fully understood from any single vantage point. The quantum properties of horizons blur the classical distinction between substance and void. The horizon isn't made of anything, yet it has temperature, entropy, and dynamics. It's simultaneously nothing, a mere coordinate location, and something, a quantum system with physical properties. This duality challenges our matter-based ontology. For human meaning and cosmic perspective, black holes remind us that the universe contains absolutes, boundaries that cannot be crossed, information that cannot be retrieved, regions that cannot be explored. Yet understanding these limits is itself a form of transcendence. We may never enter a black hole and return, but we've entered them through mathematics and emerged with profound insights. The fact that we can understand black holes at all is perhaps the deepest mystery. Why should the universe be comprehensible? Why should mathematical equations dreamed up by humans describe the extreme physics near event horizons? That gravity doesn't need to escape black holes because it's geometry, not force, is a truth we discovered through pure thought, confirmed by observation. While we've resolved the fundamental paradox of how gravity escapes black holes, this answer opens new frontiers of mystery. Each solution in physics tends to reveal deeper questions, and black holes exemplify this pattern. As our observational capabilities expand and theoretical understanding deepens, we're discovering that black holes hold keys to the most profound questions about quantum gravity, the nature of space and time, and the ultimate fate of information in our universe. The next generation of gravitational wave detectors will revolutionize our understanding of black hole spacetime. LISA, the Laser Interferometer, space antenna planned for the 2030s, will detect the gravitational waves from supermassive black hole mergers across the universe. These cosmic collisions involve black holes millions or billions of times our Sun's mass, warping spacetime on scales that dwarf anything LIGO can observe. LISA will track these mergers for months or years before coalescence, mapping spacetime geometry with exquisite precision. We'll test whether supermassive black holes follow the same rules as stellar mass ones. Do they have the same no-hair properties? Does space-time curvature scale simply with mass, or do new effects emerge at extreme scales? These observations will test general relativity in unexplored regimes. The Einstein telescope and Cosmic Explorer, proposed next-generation ground-based detectors, will observe black hole mergers throughout the observable universe. With 10 times LIGO's sensitivity, they'll detect space-time ripples from the cosmic dawn when the first black holes formed. This will reveal whether primordial black holes exist, black holes formed not from stellar collapse but from extreme density fluctuations in the early universe. Pulsar timing arrays are opening another gravitational wave window. By monitoring millisecond pulsars across the sky, these arrays can detect the slow space-time undulations from orbiting supermassive black hole pairs. The Nanograv collaboration has already found hints of this gravitational wave background. As sensitivity improves, we'll map the population of supermassive black hole pairs across cosmic history. The Event Horizon Telescope continues to expand. With new telescopes joining the network and observations at higher frequencies, we'll achieve sharper images of black hole shadows. The next decade promises movies of matter orbiting black holes, allowing us to watch space-time dynamics in real time. We'll test whether the shadows match general relativity's predictions or reveal new physics. Multi-messenger astronomy, combining gravitational waves, electromagnetic signals, and neutrinos, will provide unprecedented insights. When black holes merge in gas-rich environments, they might produce electromagnetic counterparts. The combination of gravitational wave data, revealing masses and spins, with electromagnetic observations showing the environment, will test our understanding of how black holes interact with their surroundings. Theoretical advances continue to reshape our understanding. The black hole information paradox remains unsolved despite decades of effort. Recent proposals involving quantum extremal surfaces, replica wormholes, and entanglement islands suggest information might be preserved in ways we're only beginning to understand. These ideas challenge the classical notion of horizons as absolute boundaries. The connection between black holes and quantum entanglement deepens. The ER-EPR conjecture, suggesting that entanglement creates space-time bridges, has led to new insights about how space-time itself might emerge from quantum information. Perhaps gravity doesn't need to escape black holes because gravity itself emerges from more fundamental quantum structures that don't respect classical boundaries. String theory continues to provide new perspectives on black holes. The Fuzzball proposal, where black holes are quantum superpositions filling the would-be interior, gains support from counting microscopic states. If correct, this would definitively resolve our paradox. There's no interior from which gravity needs to escape because the black hole is a quantum configuration extending to the horizon. Loop quantum gravity offers different insights. By quantizing space-time itself, this approach suggests black hole singularities might be replaced by regions of discrete quantum geometry. Some models predict black holes might transition to white holes, eventually expelling everything that fell in. While speculative, these ideas show how quantum gravity might radically revise our understanding. Laboratory analogues provide surprising insights. Scientists create dumb holes in flowing fluids where sound waves can't escape upstream, mimicking event horizons. These systems show Hawking radiation analogues and test our theoretical understanding. Optical analogues using intense laser pulses probe how horizons affect quantum fields. While not true black holes, these experiments test the mathematics underlying our theories. The possibility of creating microscopic black holes in particle accelerators remains tantalizing. While the Large Hadron Collider hasn't produced them, future colliders might reach energies where quantum gravity effects become important. Observing Hawking radiation from artificial black holes would revolutionize our understanding of quantum gravity. Primordial black holes, if they exist, offer unique probes of quantum gravity. Black holes formed in the early universe could be much smaller than those from stellar collapse. Some might be evaporating today through Hawking radiation, providing natural experiments in quantum gravity. Dark matter might even consist partly of primordial black holes. The cosmological implications of black holes continue to unfold. If our universe emerged from a black hole in a higher dimensional space, what does this mean for the arrow of time and the nature of the Big Bang? Could black holes spawn baby universes, creating a cosmic evolutionary tree? These ideas blur the distinction between black hole interiors and separate universes. Quantum computing might provide new tools for understanding black holes. Quantum computers can simulate strongly coupled quantum systems that classical computers can't handle. Future quantum computers might simulate black hole formation and evaporation, testing ideas about information preservation and the nature of horizons. The philosophical implications deepen as our understanding grows. If black holes can destroy information, does this mean the universe forgets? If information is preserved, how does it encode in Hawking radiation? These questions touch on determinism, reversibility, and the nature of physical law itself. As we push toward a theory of quantum gravity, black holes serve as crucial guides. Any successful theory must explain how gravity operates near horizons, how information is preserved, and how space-time emerges from more fundamental structures. The fact that gravity doesn't need to escape black holes, being geometry rather than force, might be telling us something profound about the quantum nature of space-time itself. As we near the end of our exploration, it's time to step back and see how understanding black hole gravity transforms our view of the cosmos. The realization that gravity is geometry, not force, that it doesn't need to escape because it's the shape of space-time itself, isn't just a solution to a paradox. It's a window into the fundamental nature of reality that connects the smallest quantum fluctuations to the largest cosmic structures. Every galaxy harbors this deep truth at its center. Observations suggest that nearly all galaxies host supermassive black holes from millions to billions of solar masses. These aren't just passive residents, they're cosmic architects that have shaped galactic evolution throughout cosmic history. The gravitational fields of these black holes, extending far beyond their event horizons, have orchestrated the dance of billions of stars. The M87 galaxy, whose black hole gave us our first event horizon image, demonstrates this cosmic influence. The black hole, 6.5 billion times our Sun's mass, anchors a galaxy containing trillions of stars across 120,000 light-years. Its gravitational field, established when the black hole formed billions of years ago, continues to govern stellar orbits throughout the galaxy. No signals need to escape the horizon. The curved space-time persists as a cosmic fossil. Active galactic nuclei reveal black holes as cosmic engines. When matter falls toward supermassive black holes, it forms accretion disks that can outshine entire galaxies. Quasars, the most luminous objects in the universe, are powered by black holes, converting gravitational energy to radiation with up to 40% efficiency, far exceeding nuclear fusion's mere 1%. All this energy comes from space-time curvature outside the horizon. The jets launched by spinning black holes are cosmic particle accelerators stretching millions of light-years. These relativistic outflows, guided by twisted magnetic fields in the ergosphere, can affect entire galaxy clusters. The black hole doesn't need to communicate from inside its horizon. The frame dragging of space-time outside creates the conditions for these spectacular displays. Black hole feedback regulates galaxy growth. When too much gas falls toward the center, the black hole's accretion disk brightens, heating surrounding gas and shutting off star formation. This self-regulation creates the observed correlation between black hole mass and galactic bulge mass. Galaxies and their central black holes evolve together, connected by gravitational fields that span hundreds of thousands of light-years. The cosmic web itself bears the imprint of black holes. Simulations show that black hole feedback affects gas, far beyond host galaxies, heating intergalactic medium and enriching it with heavy elements. The largest structures in the universe, clusters and superclusters of galaxies, have been shaped by the cumulative effect of billions of black holes over cosmic time. Gravitational lensing by black holes reveals dark matter's cosmic dance. When black holes bend light from distant sources, they act as gravitational telescopes. The distortion patterns tell us about both the black hole's space-time curvature and the dark matter distribution around it. We're using the permanent curvature of space-time around black holes to map invisible cosmic structures. The merger history of black holes traces cosmic evolution. LIGO and Virgo have detected black holes from across cosmic time, revealing how they grow through mergers. The gravitational waves carry information about black hole populations at different cosmic epochs. We're reading the universe's autobiography, written in ripples of space-time. Primordial black holes, if they exist, connect us to the universe's first moments. These hypothetical objects would have formed from quantum fluctuations during cosmic inflation before the first stars. Their gravitational fields would be fossils from the Big Bang itself, carrying information about physics at energies we can never recreate. The black hole information paradox touches the deepest questions about cosmic memory. Does the universe preserve perfect information about its past, or can black holes truly erase history? The answer affects whether the cosmos is fundamentally deterministic or whether true randomness exists. Our universe's ability to remember or forget is encoded in how black holes process information. Dark energy, the mysterious force accelerating cosmic expansion, might be related to black hole physics. Some theories suggest dark energy could arise from quantum effects of horizons throughout the universe. If true, the collective gravitational fields of all black holes might contribute to the universe's fate. The geometry of space-time around every black hole would participate in cosmic destiny. The multiverse hypothesis gains new dimensions through black holes. If black holes can spawn baby universes, then our cosmos might be one branch of an infinite tree. Each black hole interior could be a gateway to a new universe with different physical laws. The gravitational field outside would be all that remains in the parent universe, a cosmic umbilical cord that can never transmit information. Black holes challenge our cosmic perspective on time. While we experience time as flowing forward, black holes reveal time as a dimension that can be stretched, twisted, and even stopped at horizons. The universe contains regions where time flows at radically different rates. Cosmic history isn't a single timeline, but a complex tapestry of temporal flows governed by space-time geometry. The anthropic principle gains new meaning through black holes. We exist in a universe where black holes are possible, but not overwhelming. Too many black holes would make the universe hostile to life. Too few would mean insufficient heavy element production and galaxy formation. The balance that allows our existence includes having gravitational fields that operate through space-time geometry rather than force transmission. As we discover Earth mass black holes, neutron star black hole mergers, and possibly exotic compact objects, each adds to our cosmic census. The universe's creativity in forming black holes seems boundless. Each represents a region where space-time curvature has become so extreme that it disconnects from the cosmic web, yet paradoxically remains connected through its external gravitational field. Looking at the night sky with this understanding transforms the experience. Those points of light aren't just distant suns, they're participants in a cosmic dance choreographed by space-time geometry. Many orbit unseen black holes whose gravitational fields extend across their galaxies. The darkness between stars isn't empty, but filled with curved space-time carrying gravitational influence from every mass in the universe. We are stardust contemplating black holes organized matter puzzling over regions where matter loses meaning. That we can understand why gravity doesn't need to escape black holes, that we can grasp space-time geometry through mathematics and confirm it through observation, suggests a deep resonance between mind and cosmos. The universe has evolved not just black holes, but beings capable of understanding them. We began with a paradox that seemed to challenge the foundations of physics. If nothing can escape a black hole, how does its gravity get out? The journey to answer this question has taken us from the event horizon to the edge of human knowledge. From Einstein's revolutionary insights to quantum mysteries we're still unraveling. Now, at the end of our exploration, we can see how this simple question illuminates the deepest truths about reality. The answer, that gravity doesn't need to escape because it's the curvature of space-time rather than a force, represents one of the most profound shifts in human understanding. For thousands of years, humans believed forces acted across distance through invisible connections. Newton gave this intuition mathematical form, but even he was troubled by action at a distance. How could the sun pull on Earth across 93 million miles of empty space? Einstein's resolution wasn't just a different equation, it was a complete reimagining of reality. Mass and energy don't pull on distant objects. Instead, they shape the arena where physics happens. What we call gravity is objects following the straightest possible paths through curved space-time. The black hole paradox dissolves because there's nothing that needs to escape. The curvature exists in the external space-time, not as signals from inside. This truth about black holes reflects a deeper truth about the universe. Reality isn't objects moving through fixed space over absolute time. It's a dynamic, interconnected geometry where space, time, matter, and energy are aspects of a unified whole. Every mass curves space-time around it. Every curve guides the motion of matter through it. The universe is a self-organizing system where geometry and matter dance together in cosmic harmony. Think about what this means for your existence. Right now, you're not simply sitting in space, you're embedded in curved space-time shaped by Earth, the Sun, the galaxy, and every massive object in the universe. Your motion through this curved geometry is what you experience as gravity. The atoms in your body follow paths determined by the collective curvature created by all the matter and energy in the cosmos. Black holes are where this dance reaches its ultimate expression. They're regions where space-time curvature becomes so extreme that it creates a one-way boundary, a horizon beyond which the external universe cannot peer. Yet, even these ultimate gravitational objects obey the principle we've discovered. Their influence on the outside universe comes from the space-time geometry outside their horizons, not from signals escaping from within. The implications extend far beyond black holes. If gravity is geometry, then understanding the universe means understanding the shape of space-time itself. Every discovery about black holes teaches us about the cosmic fabric. The fact that merging black holes rings space-time like a bell tells us space-time is dynamic. That spinning black holes drag space-time around reveals it can twist. That black holes evaporate through Hawking radiation shows space-time has quantum properties. This geometric view of gravity has practical consequences. Your GPS works because engineers account for how Earth's curved space-time affects satellite clocks. Gravitational wave detectors measure ripples in space-time geometry smaller than a proton's width. We're not just understanding curved space-time theoretically, we're using it technologically. The philosophical implications are staggering. If space-time is dynamic and curved rather than fixed and flat, then our intuitions about space and time are fundamentally wrong. There's no universal now slicing through the cosmos. The past and future aren't absolutely separated but depend on your path through space-time. Distance and duration aren't fixed quantities but depend on the geometry you're embedded in. Black holes push these insights to extremes. At the event horizon, time dilation becomes infinite from outside perspectives. Inside, space and time swap roles. The radial direction becomes time-like, making falling toward the center as inevitable as moving toward tomorrow. These aren't failures of our concepts, but revelations about what space and time really are. The quantum properties of black holes hint at even deeper truths. If black holes have entropy and temperature, if they evaporate through quantum processes, then space-time itself must be quantum mechanical at the smallest scales. The geometry that creates gravity might emerge from more fundamental quantum structures. We're glimpsing a reality where space-time itself might be emergent rather than fundamental. Modern physics stands at a crossroads. General relativity describes space-time geometry perfectly at large scales. Quantum mechanics describes matter and energy perfectly at small scales. Black holes are where these theories collide, where quantum effects meet extreme space-time curvature. Understanding how gravity emerges from quantum mechanics, or how quantum mechanics operates in curved space-time, is the great challenge of 21st century physics. The answer to our original paradox points toward this unified understanding. Gravity doesn't need to escape black holes because gravity is the shape of space-time, not particles or waves traveling through space-time. This geometric nature of gravity might be the key to unifying it with quantum mechanics. Perhaps all forces are aspects of geometry in higher dimensions. Perhaps space-time emerges from quantum entanglement. Perhaps the distinction between geometry and matter dissolves at the deepest level. As we stand under the night sky, we can now appreciate the profound truth that black holes teach us. Those stars we see are following paths through curved space-time. Some orbit black holes whose gravitational fields extend across galaxies. The darkness between stars isn't empty but filled with the geometric fabric that connects everything to everything else. We are patterns of matter and energy embedded in this cosmic geometry. The gravitational field of every black hole in the universe, however slightly, influences the atoms in our bodies. We're not separate from the cosmos, but woven into its geometric fabric. Understanding why gravity doesn't need to escape black holes reveals our deep integration with the universe's fundamental structure. The question that seemed to challenge physics has instead illuminated it. Like all great paradoxes in science, it wasn't a problem to solve, but a doorway to deeper understanding. Through it, we've glimpsed the true nature of gravity, the geometry of space-time, and our place in the cosmic order. The answer transforms not just our understanding of black holes, but our entire conception of reality. In the end, the profound truth is this: we live in a universe where geometry is physics, where the shape of space-time is gravity, where black holes are regions of extreme curvature that need no mysterious mechanisms to influence their surroundings. The gravitational field of a black hole exists in the curved space-time outside its horizon, frozen in the geometry of space from our perspective, dynamic and evolving from others, but always consistent with the beautiful mathematics Einstein discovered over a century ago. And perhaps most remarkably, we are beings capable of understanding this profound truth, able to trace the geometry of space-time with our minds even where our bodies can never go. If you are still watching, please make sure to subscribe to the channel and give a thumbs up. And if you enjoyed this video, I guarantee you will love this other one at the left side of the screen. What would really happen if you traveled at light speed? Learn why nothing with mass can reach the speed of light, how space and time warp as you approach light speed, what you'd actually see on a journey across the stars, and much more. See you there.